All right, so hello, welcome to Calibrated, a webcast about uncertainty, Bayesian inference, and machine learning. I'm your host, Eric Novik, and I'm very excited to have Duco Veen joining us today from the Netherlands. Welcome to the program, Duco.
Hey, how are you doing?
So you're an assistant professor at the Department of Global Health at the University Medical Center Utrecht. What are some of the things you're working on right now?
There's a few bigger projects that I'm currently working on. They're not fully in the Bayesian atmosphere. That's why I'm also moving towards Utrecht University later this month also. But the projects I'm working on currently are COVID rats. So we try to actually see if using wearable devices, we were able to predict based on physiological parameters, people would be having contracted COVID before they started showing symptoms. So that was actually the goal. We set up a huge trial, 18,000 people joined. We're currently in the analysis phase, so it's pretty exciting to see if we actually manage to do that or not. That's the first big project I'm working on, and we're wrapping that up. And the other project, a big project I'm working on, is Trials at Home. And we're actually trying to run a proof of concept study in which we're trying to see if we can do clinical trials in a remote, decentralized way. So actually the participants or the patients not necessarily have to come to the sites and the hospitals, and they can still be included in trials, which hopefully would also allow a more diverse population in trials.
Great. Now you were going back a little bit. You were a psychology undergrad, right? And somehow you got interested in statistics and statistical computing. How did that happen?
So I think mostly it happened because, in psychology, there's a whole bunch of interesting research, but there's also these tiny researches that claim these huge effects and these huge impact based on very minor tweaks, let's say. And if you read Andrew Gellman's blog, you'll probably have read about a lot of them also. I think when I read those, I thought, this sounds too good to be true. It probably is too good to be true, but I can't put my finger on why it is. And that's why I really wanted to learn more about methods and statistics. I wanted to be able to better evaluate how I would approach a similar research question and how I would approach the statistics and how I should evaluate those statistics.
You do most of your probabilistic programming in STAN, is that correct?
Yeah, that's correct.
So what attracted you to STAN, and maybe you can tell us a few things that you like about it and a few things that you don't like about it.
Sure. What attracted me initially, I was running my models more in JAGs and bugs, and I was at some point actually working with very small samples and doing structural equation modeling, and it didn't seem to go so smoothly. I needed huge amounts of iterations, and the models still seemed to be very buggy. And when I moved to STAN, actually all of those issues sort of started disappearing. And what really got me attracted to STAN is actually the community. The amount of people helping out each other, sharing ideas, people from all sorts of different fields, they can help each other out because they're not competitors. They can just help each other out, making the models better. And I think the community is really what kept me engaged for STAN. The thing that's, of course, sometimes a little bit harder about STAN is when you get a new computer, you have to reinstall it. Sometimes you get these installation issues, I know at some point there were some people working on trying to maybe get a drag and drop installer. Fortunately, that wasn't funded. That would still be a huge addition for STAN.
Yeah, I know. It was. I just had my own installation issue a couple days ago. But the nice thing is that I posted it on Discourse. I think within a few hours, someone commented and told me what to do, and it was all solved. So that having an active and helpful community is definitely a great feature. So I agree. I'd like to turn it over to you now for your talk. For everyone else in the audience who's listening and watching live right now, feel free to pop in questions. We'll probably wait to answer them towards the end. So do hang around for the loop back at the end with Duco, but for now, take it away.
I already was briefly introduced, currently working at the University Medical Center Utrecht. I'll actually be moving towards Utrecht University at the end of this month full-time. I'm extraordinary professor at Northwest University in South Africa, Last year, I did the STAN governing body, and I contributed a bit to ShinyStan. I hope to be able to pick that up a little bit more again once I switch jobs to Utrecht University. So the talk today is on using expert information in Bayesian statistics. So what I'll discuss today. So I'll talk about expert elicitation, and my work has mostly been in the context of social sciences. Even though I'm at the University Medical Center now, the expert elicitation work I did was usually in the context of social sciences. I'll talk a little bit about what it is and why you would do it. So what are ways to do it, and how can you improve the quality? I'll talk a little bit about contrasting experts' beliefs and traditional data sources. I'll give an overview of 2 case studies that I worked on, and I'll provide some general reflections. What is the goal of today's presentation? It is actually to give you a little bit of a flavor of what you can do with expert beliefs in the context of Bayesian statistics also. What are some of the considerations you should think about? And I hope you get a little bit of inspiration from the case studies that I show, and think a little bit about what kind of insight experts could give you. It is by no means an exhaustive overview of all methods. It is a huge topic. Many people have worked on it. There's great work on it. And for very good overviews, I recommend a fantastic book by O'Hagan et al. From 2006 already. And more recently, Mikola et al. Provided a very nice paper, very structured, loads of references in there. So if you really want to go a little bit more into the details, those are some great reads, and they can point you to even more literature and maybe specific methods that you might want to apply. What is it? That's the first step. O'Hagan et al., they described it as the process of creating a probabilistic representation of an expert's belief is called elicitation. So we want to make a probabilistic representation of this expert belief. So we have a bunch of experts. They give you a lot of information. They shout that they know it, and we want to get them a little bit more concrete, you know. So they're shouting a lot to me, and I don't really know what to do with it. Let's formally structure that, and maybe they can give us their opinions a little bit more in the form of, for instance, probability distributions. That already provides a little bit more context, you know, it's more concrete. Then maybe I still don't really know what to do with it, but hey, I'm a step further. So why would I actually want this? Why should they give me these probability distributions? Why would you do expert elicitation? So Drescher et al., they said the knowledge held by expert practitioners is too valuable to be ignored. So we all know that there are certain people that know a lot about certain topics, and they hold this knowledge, and we don't really want to ignore it. You know, they can help shape the models, they can help define the models, but perhaps they can also provide input into priors, you know. And there might be very good reasons for eliciting expert judgments. For instance, Fang and Wang did a study about the warranty for electronic products. So you can imagine that if we take all these components separately, we might know what the life cycle is of these components. We might know how long they last. But when we put them all together in a new device, we're not entirely sure, right? We don't know how these people will start using this device, for instance, or what the interaction is between the components. And sure, we can try a lot of things, but what we don't want to do is give out hundreds of these devices, let them be tested out for a couple of years and see how many break and when they break. So experts can actually provide insights into how long these products are expected to last. And based on that, we can balance out the costs of the products and the warranty that we can provide, how long we can provide that warranty. So that might be something where expert judgment can be really relevant, you know. Another situation is an example by Hull and Smith. They want to have a location to store nuclear waste. So the storage facilities for nuclear waste, I think they said it need to last for 10,000 years. They want to do it in quite a remote place, you know, where not too many people live. So if there's an accident, not too bad, hopefully, you know. But then they want to do these remote places, but then they're suffering from seismic activities, you know. So how sturdy do these storage facilities need to be? What is still the risk of them rupturing or breaking? And you can imagine we can build 100 of these facilities and just test and try and try and try and wait and see what happens. No, we need to store the material now. So here, you know, the experts can provide insight into how sturdy these materials are, how strong these seismic activities can be expected to be, and then what the probabilities are that there's actually something going wrong. So a very good case where expert judgment can be very valuable, and maybe otherwise we don't have any data. So experts sometimes can really offer unique information. It can be used to solve problems. It can be used as an additional data source to enrich the information that is already available. Sometimes you have a data source, but maybe on particular pieces of information, there's something missing. An expert can contribute to that. And sometimes maybe, there's no data available at all, and the expert information is the only thing that you have. Then we still want to get that out in quantifiable, but we need to be really sturdy and we need to be really explicit about the methods, how we're doing it. Another reason you can also have these experts' beliefs quantified is actually to serve as quality control. We can compare the experts' beliefs and other traditional data. And if we compare them and they don't match up, we can try to figure out what's wrong. Maybe we're not talking about the same thing, or maybe there's actually a reason why experts predict something completely else than the data is showing. It can also be used to learn lessons from. Is it common? When I started out, I thought, I hadn't seen many of these models, so I didn't know if it was common. But, you start looking a little bit in the literature, and what you find is that actually, back in 2008, Cook and Goossens already had over 60,000 expert subjective probability distributions in a database. So they really did this a lot. In health economic decision models, it turns out that in 57% of those models, at least one expert knowledge elicitation parameter is included. Hadorn et al. Found, In the great book by O'Hagan et al., they describe examples in medicine, nuclear industry, veterinary sciences, agriculture. It's a wide range of topics where it's applied. So there must be something there, There's a lot of reasons to do it. There's a lot of use cases for it. So it's actually quite common. Not so much in the field of psychology, where I actually came from and where my undergrad was in. Van der Schoot et al. Found in 2016 that in all the models that used Bayesian statistics in psychology in 25 years before that, 2 used expert knowledge actually in their models. So that's very, very low. So this can mean that either in psychology they haven't been able to apply these methods, they didn't know about these methods, or maybe there's another reason, So a good thing to study and to look into. So that's partially what I did. What are some of the ways to do it? There's a lot of considerations. You can use specific or non-specific methods. And what do I mean with that? You can either have a method that is generic, that should be applicable to all sorts of problems, or perhaps you have a method that is applicable to your model or your prior specifically. You can imagine that it's much harder to find a generic solution that can be used for eliciting experts' beliefs for all problems, And so there's very many specific methods. How many parameters do you actually need to elicit? Is it just one parameter that you're interested in? Is it more than one parameter? And if so, do you want to elicit them, piece by piece, one by one? Or do you actually need a multivariate solution, Because maybe if we have all these univariate priors elicited, actually in a multivariate solution, they would behave quite differently. We can consider if we want to do elicitation directly or indirectly. And what I mean with that is we can ask about the parameters that we are interested in immediately, or via another way around. Perhaps they can predict data, They can give you all sorts of examples of observations they would expect, and from that we can infer, for instance, the mean of that. Quantile elicitation is much more direct, so I would ask, what is the 5th quantile of this parameter? What is the 95th quantile of this parameter? It's much more directly about the parameter itself. There's a consideration if we want to have multiple experts, if we want to do that in a group setting or individually. In a group setting, you might have a dominant person, and this dominant person might actually sort of silence other experts and just say, this is it, So sometimes you want all the experts individually to provide you first with information. And if we have these multiple experts and they all provided us individual information, do we want to aggregate that? Do we want to do that mathematically? Do we want to weight all experts equally here? Or do we actually want to have interaction, Can they adjust? Can they know what the other experts said? Can they adjust in multiple rounds, So those are considerations make when you do these expert elicitations, and it can be very hard because there's also constraints there on your budget, on your time, and also constraints there are how much training is there. It's very good to train experts when you want to do an elicitation. Maybe domain experts don't fully have the statistical knowledge that you need for them to express their beliefs in this probability distribution. So we need to train them on that. And how much time would that cost? So are your experts also statistical experts? So these are all sorts of considerations that you really need to take into account when doing an expert elicitation study. So you can see there's a lot of things to tweak, and that's why it's very hard to find a generic answer on how to do it. But there's many people who have done it, and there's many solutions. When I started out, one of the things that I wanted to immediately go and do, one of my colleagues showed me what they did before. It's the picture on the right. They went with a piece of paper towards experts. They got stickers. And these experts, they would put the stickers on the piece of paper. They had 20 stickers, each one representing 5% of their beliefs, and they would take this piece of paper home. They would take it to the office, they would scan them, and they would try to fit a probability distribution to what the experts had told them. We wanted to digitize this process also because these stickers are not what we're actually using. It's what the input from the experts that they gave us, but we're using something that we fit towards that. So if we do that instantly and we digitize this process, we can actually feed back to the experts, this is how we're interpreting what you gave us, and do you agree with that interpretation? That's the first thing that I really wanted to do. And why is that important? So Goldstein and Rothschild already found that the intuition of even lay people improved through graphical elicitation techniques. So if it's already improving the intuition for lay people, it might also very much help for experts. The second part is what I told before, we're really interpreting the expert's belief, and we need to show how we interpret it. And the third part is also, it's a dialogue. If they don't agree with how I interpret it, that's when I know, and I can immediately get them to adjust it. So it's more direct, I get more feedback. Well, this can of course be done by creating some pieces of software, and that was already recommended also by O'Hagan et al. To do that more often. So I started wondering, is this done often? How do people do it? And we did a review of software use, somewhat systematic. We pulled out all the reference to O'Hagan et al. We did a Scopus search. I looked at all the packages on CRAN, that was already a while back. Very soon we came to the conclusion that there's a few people who've attempted more generic solutions. The most recognizable, I think, is Shelf. It's also in our package. Nowadays, they also have a Shiny app for that, and Match was a web-based version of it. They were quite good, but they're the most generic. But what we saw is that actually most people programmed their own elicitation software, And the reason for that was that it was usually very much context specific. They wanted to tweak a little bit, or they wanted to align more with the experts that they were using. And this is something that we also noticed that was sometimes needed. So we saw a lot of single-use applications being built, and with cause. Besides the software, there's all sorts of other things that you also can think about to improve the quality of an elicitation that you're doing. There's a great literature on heuristics and biases. Kahneman and Tversky, of course, a lot of work on that. O'Hagan et al. Provide a very nice overview in their book. So definitely, if you want to read more on that, they provide nice overviews, very good references. But you want to avoid triggering some of these heuristics and biases. You can imagine that if I talk to an expert and at some point I start name dropping some numbers, that actually creates an anchoring bias. So anything they'll do afterwards actually becomes closer to this number, Another thing is an availability heuristic, If people think of a very extreme case, then their estimates will be pulled more towards that extreme case. So you want to sort of avoid them to trigger specific outlier events, shall I say, in their mind. Another thing to do is you really need to train experts and facilitators. And what do I mean with facilitators? Those are the people trying to get the experts to quantify these beliefs, The reason to train these people also is to standardize their responses. We have to make sure that if we do multiple experts and give elicitations to multiple experts, if they ask certain questions, they need to get the same responses, because that's the way we ensure that they also actually answer about the same concepts. When we do this in a face-to-face setting, it can improve the fact when clarifications are needed, it can be improved, you know. Nowadays, I'm also doing this via the internet. We can also via the internet, of course, do a lot. So maybe that's also a very good solution, but at least a facilitator being there can improve the quality of the elicitation. I'm going to talk a little bit more about what we did. As I said, we wanted to at least digitize it. And what we found is that the experts that we were using or that we were talking to, they actually sometimes had difficulty with the concept of hyperparameters and the uncertainty related to that, you know. It sometimes happened that they were providing us distributions of the data that they expected and not actually about the hyperparameters. And so direct steps were not always clear cut for these experts, and that didn't always help their reasoning. So we tried to align more with their reasoning, and that's why we cut the elicitation into smaller steps, you know. So we tried to combine direct and indirect elicitation. So what we did is actually we tried to get the experts to first predict what type of data they would be seeing, you know, what are the examples of the data they would be seeing. Based on that, we can of course then extract, for instance, the mean. Okay, so you're telling me based on what you know and what you see and what you expect that this is approximately the average that you expect. And then that's the next step. Then we go directly asking about their uncertainty about that estimate. So we took a little bit smaller steps to help guide the experts a little bit more. We called that a 5-step method. You know, it's nothing very special. It's just the philosophy was to cut it up into smaller pieces for the experts to help align more with their reasoning. And as not all experts within social sciences were per se also experts in statistics, this helped for some experts. You know, there's also experts who say that wouldn't have been necessary, but you know, it's nice to at least make sure that we're all on the same line and we get the distributions that we want. So the first step, you know, that was eliciting parameters using the trial roulette. I'll show a screenshot of an app that we used later. It's the direct elicitation. It's very much in line with, you know, the stickers that we saw before of my colleague, except now digital, and you get immediate feedback. From that, as I said, we extract the mean and we elicit scale and shape parameters. So we ask for lower and upper bounds from the experts. Again, we provide feedback on how we interpret this, and we use that elicit distribution. So that's the proposal that we made on how to do it for ourselves. So here's a visual, you know, for the first step, we put these stickers. And in the second step, we provide direct feedback on how we would interpret what they're giving us as reasonable lower bounds and upper bounds related to that estimate. And they see the distribution that we were using. And here we were using a skewed normal distribution. The fifth step, use that distribution. And now use that distribution, but for what, you know? I mean, we need quality control. There's a burden of proof, and the burden of proof of the quality for expert elicitation is actually quite high. So we need to make sure that people have confidence in the things that we're using. You know, so that's that's the next part. So how do we get this quality control in place? So we thought maybe if we contrast the experts' beliefs and data, then, you know, we can sort of verify and see if experts say similar things as data that we usually collect, and that might enhance trust in the methods that we're applying, you know. There's an additional way which you can do quality control, and that's actually Cook et al. They use that a lot. They call it the classical method, and they employ calibration questions. So they ask a whole bunch of other questions they're not really interested in, but they're closely related to the subject. And to those calibration questions, they actually know the true answers. So if experts provide answers that are very close to those true answers, you would rate experts as having a lot of knowledge, you know. And if they're further off, you would downweigh them if you want to use their listed opinions later, you know. In psychology, we found the topics that we were working on, it's actually quite hard to come up with questions that we have the true answer to, you know. Psychology has a lot of latent constructs that we're working with, and what are calibration questions that I can ask to determine if somebody is an expert in depression or something like that. It's very hard to find quantities that we know have a specific value, and the expert should also know that. So these calibration questions didn't really, for us, seem to be a very good option. So maybe we compare the priors that we elicit actually to the data that we also can potentially collect. We can actually see if there's a prior data conflict. So, these experts, they give us a bunch of probability distributions. And if an expert is actually quite close to the data, so in red, let's say that there's a distribution of the hyperparameter as would be given to us by the data, and in blue would be, what information the expert provided regarding that same hyperparameter. In this case, they'd be quite close to one another, so you'd want to conclude that there's agreement between the two. If they're much farther apart, we want to conclude that there's disagreement. So actually the experts and the data are saying something different. What's something that we can use for that? We went looking a little bit in the literature, and Bousquet had a very nice article in which he proposed to use the following. We can use Kullback-Leibler divergences. It's a visual representation. Kullback-Leibler divergence in the end is one number, but you can see how well the expert approximates this distribution, that the data would have given you. If they're quite close, then actually the number is low. And if they're far apart, the Kullback-Leibler divergence is much larger, and we get to a much larger number. Bousquet said you can take a benchmark prior. This benchmark prior should not contain information, basically, or very little information. And if you compute a posterior based on that and the data, then you get a posterior distribution that actually represents the voice of the data, let's say. We can compute a Kullback-Leibler divergence between the posterior and that benchmark prior. So if I'd not given much information or almost no information, how large would that divergence have been? And you can also get a Kullback-Leibler divergence for the posterior that we just got from the data and that benchmark prior, and then relate that to a candidate or expert prior. How much loss of information is there if we say that the expert is trying to approximate this data? If you compute a ratio, if the ratio is smaller than 1, you say the expert is actually closer to the data than a benchmark prior that should contain almost nothing. If the ratio is larger, then the candidate prior or the expert's prior is actually not a good representation. There's prior data conflict. Giving no information would have been preferable in terms of loss of information. You can either be in disagreement, in prior data conflict, or in harmony. So there's no prior data conflict, That does leave a choice of benchmark. It needs to be low informative compared to the data. The data should really overwhelm it. There can be practical choices. There can be all sorts of things to work out here. But usually if you just take a very wide uniform prior, that's what Bousquet initially recommended, then that contains almost no information, and it will certainly be overwhelmed by that data. And when we have multiple experts, what we can do is actually we can compare those Kullback-Leibler divergences to that data directly, or we can compare them all to the benchmark and see who's actually quite close, who's doing quite well, who's not doing so well. And I would also suggest to always look at the data visually too, because you can be in a setting in which we're trying to compare to see which expert is doing better and is better approximating the data. Is that the expert who says, I'm very uncertain, I'm going to give a very wide prediction? Or is it a more certain expert who's closer towards the data, Or maybe when they're certain but they're a little bit off, it's actually worse. But by looking at the data, you can also see when the experts are actually agreeing with one another, and there's the data on the other spectrum, and then probably we're not talking about the same thing. So we always need to be careful. As I said, the burden of proof for the quality is also with the people who do the expert elicitation. So we need to verify that we're talking about the correct concept also. Now I'm going to talk about 2 case studies that we did. I hope you already get a sort of idea and a feel that there's a lot of things to tweak, to turn, a lot of choices you can make. And I'll talk about 2 case studies that we did to try and see if the elicitations that we were doing were providing us relevant information, and if we can have some sort of confidence in the elicitations that we're doing. So the first context was actually with experts in a financial institution. And we wanted to know how good these prior beliefs are of these experts, They were regional directors and they had a bunch of people working under them and they all needed to bring in money. And, these directors should have a very good idea about what the next turnover or the average turnover per professional actually is going to be in the upcoming quarter. They are experts concerning market opportunities, market dynamics. They should be estimating the capability of their professionals to seize the opportunities very well, They were used to providing single-digit estimates, A little bit of a problematic thing also there is that if you ask these people how much money is going to come in, it's also going to relate to their bonuses. So, there's an incentive for them to lowball sometimes a little bit. That's why also this financial institution wanted to collaborate. What if we now get them to specify this actually together with uncertainty, So how about we get them to specify their beliefs in terms of priors? And how about then, if we want to verify if they're doing well, and also we want to see if this expert elicitation tool is doing well, we now collect the data of the next quarter that's coming up. And we want to see if that's actually close to one another, So the beliefs that they were having, which were in principle could have been used as prior information, were they actually close to what we saw turning up at the end? In red, you see the data that was actually coming in. And in blue, you see the different, in different dashes and dots, you see the different distributions that the experts actually provided us. And in very light brown, there's a big uniform prior there somewhere that was used as the benchmark, So what you see is actually there's a few experts quite consistent with one another and quite consistent with the data. And it seems that one expert is actually quite a bit off, and this is a visual way to look at it. So it seems that at least the experts and the data were probably talking quite a bit about the same thing. That's a good, first sort of check to pass. We can get these cubic library divergences. Again, it's a visual representation, but here you get the actual numbers. And then there's also a cubic library divergence for the benchmark. And you can compute that ratio and you can see who's in conflict and who's actually not in conflict, So there's actually one expert that's very close to the expert one. There's an interesting thing going on with this benchmark prior and the cubic library divergences. If you look at experts 1 and 3, we would actually conclude that the expert 1 is it's a little bit hard to see. Maybe you can see my mouse. That's this expert. So he's here or she is here, and the other one is here. And the one that's a little bit more uncertain is getting quite a low cubic library divergence, and the other one is getting much higher cubic library divergence. And the one we would conclude to be in conflict with the data, and the other one not. So it's also a sensitive measure, so it's also taking it with a little bit of a grain of salt, because they're just missing the target, and so they're being penalized quite heavily for that. But it gives us an indication which experts are closer to the data, and so which would maybe have a little bit more of information for us. We would have liked to do this iteratively. We would have liked to set them together in a room, learn from one another. Why did you predict this? Why did you predict that? Unfortunately, we were not allowed to do this by our ethical committee. And that was a big shame, and I'd still like to do this very much, because I think this is where expert elicitation, regardless of you using it as priors in Bayesian statistics, if you get experts to quantify their information, if you compare it to data, you can learn, you can see, you can try to understand why one expert was saying something differently as another, And that's where I think expert information can be very, very valuable. It's in a learning process. We had a bunch of experts. They were saying a lot of stuff in the offices. We got them to quantify their uncertainty and probability distributions. If we want, we can rank them, or we can at least see who was closer to the data than the others, And from that, hopefully, from our confusion, we start to learn things. We get new ideas. We can make, we can enrich our knowledge. And this is really where experts can have a lot of information for us also, qualitatively very often. So the second case study, I'm warning the graphic after this is going to be a bit bit shocking, and it's a bit harder for me now since I have a 2-month-old son, and it's about burn injuries with little children, the impact of pediatric burn injuries. So we went from this simple case study in which we actually thought, there's reasonable evidence to suggest that if we cut this elicitation up into smaller steps, the expert might be quite close to the data. So maybe it's working quite well, splitting that up using 5 steps. Now let's see if we can use a more complex model and apply the same sort of framework, So we were looking post-traumatic stress symptom development in children with burn injuries. This is one of the reasons why expert elicitation can be very valuable here, is you can imagine that there's not a whole lot of little children that get these burn injuries. And we don't want that. We don't want more data. But now we're doing analyses on large groups from 8 to 18-year-olds, that's also the data set that we had to compare it to. But you can imagine that children from 8 years old and 18 years old are actually quite different. So perhaps if experts are very good in this topic, we can start to look at smaller subgroups and supplement the data with expert information, It's really about the development of post-traumatic stress symptoms in children with burn injuries. They were between 8 and 18 years old, minimal of 24-hour stay in the hospital, and a minimal percentage of the body burned of over 1%. And we use self-reported post-traumatic stress symptoms as for the reference data set, let's say. So the experts that we got 14 experts for this study, 7 nurses who were specialized at working with burn injuries. It's the only work they did. They worked in the Free Dutch Burn Institutes in the Netherlands. We went to all of them, and these nurses only worked with these types of burn injuries. There were 7 psychologists that we were also using as experts, and these were the psychologists actually working with these children, to get to talk to them, to help them through the difficult periods, Another thing that we did in this study, we actually used audio recordings of the elicitations for qualitative information. So we can compare what we did to data that were actually in existence, but we can also hear what the experts were saying while they were doing this. And we asked them to say everything they were thinking out loud. So we can see maybe if we were triggering some of these heuristics or not, We use this 5-step method again. And we try to adjust the method for the elicitation of a hierarchical model. So I'll show what I mean. So this was oh, sorry, Eric, you were asking, what do you mean by a few data points? Few relative to what? So, it's always in comparison to the complexity of the model, That's always the case if you say that there's little data. There's only little data if the model is more complex, and there would have been, if there was more data, we would get more certain estimates, The models were relatively complex to the number of data points that we were having from these children and the number of children that we were having. We can, of course, simplify the model. That's also not always the thing that we want to do because, there's a reason why we want to go for a more complex model. Also, expert elicitation. If you want to use expert information as priors, it's always in the context of the model, but also, it's in context, So if you have an expert belief and an expert prior, it can be very certain compared to the amount of information that you have in a likelihood, for instance, or it can be very vague. So it's always in context. So we tried to extend the model. The model that these people were using for these types of data was a latent growth curve model. It's basically what is the starting point of the post-traumatic stress of these children and how does it change over time? So what is the slope? And, we're having a lot of these children. So for all of these children, we're having these 4 measurement points. So we can estimate all of their, intercepts and all of their slopes for the progression of their post-traumatic stress over time. And we were interested to see if the experts could help us provide information regarding the hyperparameters and the means for the intercept and the mean for the slope, Small steps. Let's see if this is something that we can get to work. The first step that we actually took is, again, to ask them to sort of predict data. Just give us a bunch of trajectories, how these children would progress. Will they start high? The post-traumatic stress list that they were using had a score ranging between 0 and 100, which was convenient. So that was actually also the language in which these people were used to talking about it. So it should be okay for them to predict data in this sense. So they would draw a bunch of lines, From that, we can of course say, okay, this is the mean trajectory that you're giving us. So you're saying that on average, these children will start at approximately this amount of post-traumatic stress. And the change over time, there was a fixed period. I think it was 12 months that they were looking at, is on average a decrease or an increase of this amount, Okay, that's a verification. If they agree with that, how we interpret that, then we go to the next step. They provide uncertainty about that starting point. Here you see if they provide the lower and upper bound for that starting point. We see here the probability distribution that we use for that mean intercept. You can see the dark shading, it's uniformly. They're saying only a difference in change about the starting point. So, we haven't changed anything about the slope so far. So no uncertainty added there. So everybody has the same slope, or the same slope is still estimated, In the next step, if they agree with this representation, we actually add the uncertainty about the slope. On average, do you think on average they can only decrease? Or do you think there's also still a possibility that on average they actually might be increasing? This is just a toy example, but we did this for a lot of experts. In the end, we provided them an overview of everything that we asked from them, And then we started looking at all the different experts and actually trying to aggregate them, weighing them equally in the first instances. But what we saw was quite interesting, where in the other example, we had experts that were quite close to one another. We saw here that the experts were, well, not all over the place, but when you look at the intercept, it ranged from starting point of 20 to almost 50, And when we look at the slope, we really see people having strong negative slopes and people being very sure about a small positive slope. So, if we look at these individual priors, they're very, very strong. They're very opinionated. There's very little certainty in there. If we would aggregate the experts, we see a much more balanced out story. We see a much wider prior, But yeah, there's the most interesting part here was that actually, when we look at the 7 nurses and combine them, and we look at the 7 psychologists and we combine them, we saw different things, So the nurses actually thought that the post-traumatic stress started somewhat higher, and that it would actually, very often, they would think it would increase. While the psychologist said, no, it starts much lower and it actually decreases over time. Here's a point where we didn't look at any of the data available to us, but just looking at what the experts were saying to us, we can see that there's already some sort of thing going on in between the experts. So we have to get them also together to sort of see and verify what's up. Are they talking about the same concept? And this is where the audio recordings were also very useful. I'll circle back to that in a little bit. So here we see actually the cumulative densities for these, for these experts. If we compare them to the data that we had, the data was much more precise. It was also collected over quite a long period of time. So we had quite a few cases, luckily. But it's not like the experts were super close. The psychologists, they sort of overlapped with what the data was telling us. The nurses a little bit less. But would I now want to see if I look at what we got as priors from this expert elicitation process, would it install confidence in me that this method was the way to go and to use these priors for future studies? No, not yet, but it definitely, it still provides us a lot of information, just maybe not to put in our statistical models. So we can, of course, calculate all these cubic library divergences. And if you then look at the nurses put together, or all of the experts together, we get these quite wide priors, and they're not doing so bad in terms of divergence from the data. But the individual experts, there's one or two experts that are doing pretty well, but mostly they're a little bit off, Yeah, it's not very hopeful, we thought, or it's a little bit disappointing. Let's phrase it like that, We listened to the audio recordings, and what were some of the things that we were seeing, First, are people referring specifically to all sorts of concepts of post-traumatic stress? Well, all the psychologists were actually doing that in the audio recording. So they were really hitting like all the concepts that are related to post-traumatic stress. And only 2 nurses did that, but a lot of them actually mentioned acute stress. So the things that you see when you're currently at that point treating patients. So perhaps, if we would do a future iteration of this, we would have to more iterate about the concept of post-traumatic stress and what is actually not included in that, Another thing that happened, and that might explain why the nurses really also thought that it might increase over time. The nurses, there were 5 out of 7 nurses that actually expressed very severe cases that came to mind, Even though it's something that we don't necessarily want to trigger in an elicitation. We saw that it was one of these heuristics that was being triggered. And maybe that actually led to an overestimation of the amount of post-traumatic stress. And there were also actually a few psychologists who reflected on the linearity assumption of the model. So, we took a model that was used in the literature, but they were also saying maybe there's actually a quadratic term needed in here, Usually it goes up a little bit first and then it goes down in the end. Also, that's one of the things the audio recordings really valuably added here. A few of the experts actually actively reflected back based on the visual representations and feedback that we got. So they adjusted their input based on us saying, okay, this is now how we interpret it. So that's actually a nice thing, one of the things that we wanted to reach. So that instills confidence that this use of software is a good idea. And, one of the experts stated that although they were sure about the direction of the trajectory, they felt very sure about the associated numerical representation. If that is the case, then you would have expected them to give quite a wide range. Yet that didn't happen. So this is one of the things that we had to think about. And one of the reasons why we're thinking that sometimes it's also difficult and maybe we should have done more training with them, And that's also constraints that you sometimes have in your project. There's not more budget, there's not more time, So perhaps if you can't do enough training, you shouldn't do it. This is most of the things that I wanted to show you, For single parameters, there's quite a hopeful scenario, For the more complex case, we already were seeing quite a few struggles, So I'm not sure that it's always a good idea to implement this. So what are some of the general reflections that I have on using expert information? So more general, expert elicitation is not so common in psychology. Perhaps having a lack of calibration questions can make it harder. Perhaps the fact that we talk a lot about these latent constructs, unobservables or, depression, post-traumatic stress, they can be hard concepts to put numbers towards. So maybe perhaps also for experts, it's not always as easy to provide a probability distribution here. As I said, how much training do the experts need? Experts have always domain knowledge. They might not have a lot of statistical background. And so maybe there's a lot of training that is necessary. And you need to see and figure out if that is worth the effort, What elicitation method will actually suit them? Do we need to ask them directly about certain quantiles of a hyperparameter, Or should we actually ask them to predict data? Maybe that's more comfortable to them. Do we require group consensus? Do we want to have all these experts in one room? Do we want to have iterations, or do we want to mathematically aggregate them? These are things to really consider. Iterations and learnings, as I said before, I think it can be very valuable. If experts can share, why they had certain beliefs, it can really help other experts to refine also their own thinking. Also, what is the goal of the constructed probability representation? Maybe it's more suitable for some goals as others. Do we want to use it as the prior information in a model that we're going to update with data? Then there's really this burden of proof of the quality of this prior. And do we feel confident enough that for this specific problem and case, we actually have a well enough method that these priors should be used, Maybe in a learning goal, it's more suitable. So I'm not aware of any tools that will uniformly help you to construct priors based on expert beliefs or judgments, There's a lot of different ways for different problems, you know, and there's definitely very good tools, and also they've shown to be good, but a uniform solution, I think, is very hard because of all the little tweaks and knobs and you know, all the different inputs that you need, and also the differences in the experts, you know. The second reflection that I have there is also, you know, do we always need this full expert prior? Do we really need them to give a very specific piece of information and say it will be approximately this and that? Or will it already be super helpful if the expert helps us think through the models, constrain the plausible parameter space? You know, that can also already make your priors much more smaller. Finally, do we have the same nomenclature as our experts? So, you know, do we have the same terminology that is used? Do we understand one another? You know, this is also something to really make sure that it is aligned, and that's very important in the training phase, you know. Some critical notes on the prior data disagreement measures that I also showed, you know. This is in these examples, it's based on one sample of data, and you know, you're not sure if that sample of data is really representative. But if you could do this in an iterative way, you know, we get experts to provide these priors to get these predictions. We collect some data, we contrast the two. We do this again. We have a session with the experts in which they're informing one another of why one was making certain choices, why somebody else was making choices. We inform them who was closer or not, so maybe they can have learnings. And at some point, you would hope to have convergence, you know, so that the experts and the data are really in agreement. That's also one of the things where I think it can be highly valuable. And maybe not per se always as priors in statistical models that we're updating. Are the benchmarks that we're using meaningful in these prior data disagreements? You know, you can make them meaningful, but then what do I do with that posterior, you know? So that's also something to critically think about if you want to use these measures. So I started off earlier with a quote by Drescher et al. That said, the knowledge held by expert practitioners is too valuable to be ignored. But you know, I should have been a little bit more full in what they were saying, because they were also adding, only when thorough methods are applied can the application of expert knowledge be as valuable as the use of empirical data. The responsibility for the effective and rigorous use of expert knowledge lies with the researcher. You know, and reflecting on my own case studies that I worked on, I think for simpler models, I can show that these expert knowledge can be represented in a nice, valid way, you know. But for the more complex cases, it sometimes also maybe is not so suitable. So I think this burden, it can be quite high, this burden of proof of how rigorous the use of expert knowledge is. And yeah, we really need to show all the things that are being done to enhance that trust.
Thank you, Duco, for this great presentation. We have a few questions, and I have a couple myself. First one on the languages front from Surnjani. If you're aware of any of Python packages for expert elicitation, I think this the one you mentioned, Shelf, which I've seen as an R framework. If that's
yeah, so I'm not aware of any Python packages, but for instance, that Shelf one definitely comes with an interface in Shiny, you know. So it's I think if you would install that package in R and run one line of code, you would get a Shiny interaction with it, you know. So I'm not aware of any Python packages, but it can be fairly easy to get towards these things. And Match, as I mentioned before, there used to be a web page on it. I'm not sure. I haven't checked if it's still live.
Okay, great. So the next question is around the aggregation of different expert priors. So this person asked, how do you do this aggregation? Is it like averaging priors or something like that? I think there are a few methods for it, but maybe you can comment on how you guys did it.
Yeah, so there's definitely a few methods to different methods to do this, let's say, you know, and averaging these priors, that's definitely one way to go. Another way, what they're trying to do more in a classical method, for instance, is actually assess the quality of the experts, you know, the knowledge of the experts, and based on that, provide weights on which how much these experts should be represented in that overall prior, you know. So there's definitely different ways to aggregate them, and there's differences in whether or not you want to basically balance the experts based on some criteria.
Thanks for that. Here's a question from Angie Moon. So her question is, can we communicate the need to consider computation related to elicitation algorithm with domain experts? For instance, the quality of inference differs greatly depending on how zero avoiding our prior is for the heterogeneity in a hierarchical model. However, I find it difficult to deliver this to domain experts. Close the gap between modelers and algorithm designers. Any thoughts on that?
So that's a little bit where I went towards with what is the goal, you know? Is the goal of your prior elicitation to really let the expert voice their opinion? And if they want to voice their opinion, then it might not necessarily, coincide with these computational constraints. But if the problem is you can't get your model running, you need more information, and you can get experts involved to show you, to tell you what reasonable constraints on those parameter spaces are, then you can definitely get these things much more involved, you know. So I think it depends on the goal and the context what you're doing. If you're really trying to express the belief of the expert themselves, if it can already be represented, you know, in a probability distribution, then you should let them voice it as they, as they feel their beliefs. But if you very pragmatically want to use domain knowledge to constrain your parameter space, then I think that's a much more suitable purpose, you know.
Okay.
Then it's much more suitable to have that discussion and to inform them about it.
Another follow-up question relates to the relationship between doing this prior sensitivity analysis with the expert elicitation. Do you consider that sort of part of the same framework, or?
So sorry, if do I understand correctly? You're asking if prior sensitivity analysis is within the same framework as expert elicitation?
I believe that's what the person posing the question was asking.
I think it's usually a good idea to do prior sensitivity analysis, and if you're using expert knowledge, that's definitely also the case, because you also want to see, if you're using this expert knowledge, how heavily does it influence your model, you know? Am I really getting pulled towards the estimates that my experts are providing me? Or is the data also, you know, contributing in the posterior quite a bit? Or I think prior sensitivity analysis is always a good idea. And if you use expert knowledge, I definitely also recommend doing it.
Okay. Damian Grant asked a question, which I don't understand exactly what he's talking about, but maybe, so I'll read it. Is there a mathematical relation between the KL divergence metric you used in their scope? I don't, do you know what he's trying to get to? Maybe Damian, you can clarify what you mean, or?
So I think I know what he means. So, you know, they're asking these calibration questions, and they're using it to construct a measure based on which they weigh the experts. You know, if they're closer to these calibration questions, then they get weighted higher. You know, they are provided more weight in the final distribution that is computed. So I'm not sure actually if this is done by Kullback-Leibler divergence. It also probably depends on the, you know, the parameters that you're using, the questions that you're using in there. I'm not sure which one they use by heart.
Okay.
But I think you can use it to the same purpose.
So Ben Lee asks, do you have any thoughts on how to deal with expert elicitation occurring after data is collected, and how this data might influence their opinions, how this might be dealt with?
Well, you know, if the experts already saw the data, it feels a little bit like double dipping, you know. And then also there's degrees, you know. If we use a more complex model and the experts have seen, you know, for instance, some of the raw numbers, the raw data, that might not necessarily be a problem. But if you already ran your model, they saw the output of that model, and then you're trying to get that to specify a prior, that doesn't seem, you know, as the way to go. But that would be my idea. You know, if you already ran your model, the expert already saw that information, you know, it's like asking them to recall what they saw.
Right.
And to ask them if they agree with it, you know. I'd rather than ask them beforehand, contrasted it to the data that you actually got in, and then see if it actually lines up, you know. That seems to me more of the right order of things to do.
Great. So I'll ask the last question. Is somewhat broad, and it's about sort of costs and benefits. And I think you kind of alluded to that at the end in your remarks. But how should we think about, or do you have an opinion right now in terms of like the costs of doing this and the benefits that you would ultimately derive, right? Because any method that you use has some costs to them. And like for us, for instance, we do a lot of Bayesian models, but we haven't done this. And I often think that we should, but then it means that we need to spend time doing this. So do you have a sense of sort of the effort on the effort side of the equation, like how much time, I mean, people are involved to get something like this done for like a moderate project or something like that? And what are the relevant benefits that you think would?
I think it can be quite costly. You have the experts that have the statistical knowledge involved. You also have to have the domain experts involved, which are also usually highly specialized individuals who have very costly time. It really depends on if there is another source of information. If the experts really provide something additional, something unique, something that you can't find in another way, there's high motivation to do it. And if there's high motivation, or motivation may be a bad word, but there's a very good reason why you would need this expert knowledge. There's no other way to get certain parts of this information, and this is the best thing that we can do to get towards a more informed opinion, then it's really worth that cost. But if there's an alternative way also in which we can get towards that additional information, you need to contrast how sure you are that your elicitation methods are good. And the more complex your model becomes, the harder it is, the harder it is to the alignment of the experts and the statistics.
Let me ask it a little bit of a different way. Have you tried, or do you think it's a good idea to do an experiment where you would essentially, for the same model, you would ask the experts, try to do the solicitation, get all the information, and then do the model checks and all that, and then have not do that at all, and just sort of try to come up with your own priors, like most of the time what we actually do, and then see how much better, in some sense of better results we get for that particular model. Is that something that's part of the research?
Yeah, so of course I played around with that a little bit. Especially the case study that you saw where I had these nurses and these psychologists. We know the range of the methods that are used. We know the range of the questionnaire, the scores that can be there. The score ranges between 0 and 100, so the intercept cannot be anywhere outside that range. If we start all the way on the top at 100, it cannot go down more than 100 over the entire range of time. It cannot go up more than 100. If we constrain this plausible parameter space, we actually have quite a detailed and informative prior, just by thinking about what is used in the collection of the data, what is the scope that these values can take. If you then looked at it, if you look at the individual priors of these experts, they were quite, spiked, quite precise. If you would use them, of course, you get much narrower posteriors, but they lean very much towards this expert. If you take those combined priors from all of these nurses or all of these psychologists or all of those experts together, it's not so much more informative actually than that uniform prior that we could already have placed on that parameter space, just by thinking about what is actually being used in the data collection. Yeah, there's definitely a lot of room already, and we also need domain knowledge for that, so you always still need to collaborate with all of those experts, but maybe we don't always need to go through the whole process of formally eliciting precise priors.
Yeah,
that was basically the conclusions that I saw mostly when I was doing this in my PhD. I saw a lot of opportunities in learning, a lot of opportunities to enrich the knowledge that we're having from the data and the expert and aligning them. But using them as priors in the context where I was working was not always the best idea, I think.
Yeah, I guess if we can elicit the priors and the likelihood and make our experts do all the work for us, then we no longer need to do our job. So that would be nice one day. Maybe
Yeah.
you can come up with some AI solution for it. All right. Well, thanks a lot, Duco. Appreciate it. Great talk. And we'll see you guys next time.
All right. Thank you so much.